Any questions about anything? Well, at the end of last hour, I was got in kind of a rush, sort of blasted over this thing that I wanted to emphasize. So at the end, I was demonstrating the differentiable inverse function theorem. Last week, I had done the continuous inverse function theorem, which was about a monotone increasing function. I did the increasing case. The decreasing case is similar. But the continuous version was I had a monotone increasing function that was continuous. Then the theorem said that the inverse was also monotone increasing and also continuous. So that was the continuous version. The differentiable version now is that when I have a function like that, so it's monotone and continuous, if it has a derivative at a point, then the fact is the inverse is differentiable, and the derivative of the inverse satisfies this formula. I'll explain this formula in a second. It will make it easy to remember. Okay, so there's two conclusions. One is that the inverse is differentiable at f of c, and that a derivative at that point satisfies that equation. So part of the conclusion is that f inverse prime exists at f of c, and that formula holds. Okay, that's from last time. And I started the proof and mentioned that the hard part of the proof is knowing that the inverse is continuous. But we got that. So, knowing that, I'm going to write G. So let's see up here in my graph. I'm going to write G of x is equal to f inverse of y. What am I writing? I'm sorry. G. I'm writing G as f inverse. Okay. Okay, so knowing that the inverse, G, is continuous, greatly simplifies, makes this a snap. So it makes the proof a snap. And I was trying to demonstrate that at the end last time. If I write the difference quotient for the G thing, for the G derivative, I'd have G of y minus G of f of c over y minus f of c. That's the derivative. And I write out that difference quotient, and I invert it. And then I start writing, let's see, y is equal to f of x. So x is equal to G of y. So if I place y by f of x in that difference quotient, and x, and write the G of y is equal to x, I get the difference quotient for the derivative of f. And let's see, I told you the next thing I need to use now. So G prime of f of c is going to be equal to this limit of that expression as y tends to G of c of the difference quotient. Okay, but now I think about it. I know that the, what do I know? I know that the inverse is continuous. So So here's the things I know. The inverse is continuous, so I know that g of y tends to g of f of c as y tends to c. Because I know that g inverse is continuous. That's the hard part in the proof. Okay, and let's see, what else do I know? Jeez. Let's see, x is equal to g of y and so that goes to g of f of c is c. Okay, x is g of y, and that's going to go to g of f of c, and that's equal to c as what? Doggone it, as y tends to f of c. And so x equals g of y goes to g of f of c, which is c, as y tends to f of c. And so that difference quotient, what I need to see to make that thing make sense is that x goes to c so that I can calculate that derivative right there. So this thing is exactly what I need. I need to see that x goes to c as y goes to g of c. And that's the continuity of the inverse. So the difference quotient tends to 1 over f prime of c because of that formula, from formula above. Okay. Let's see, part of the conclusion, part of the assumption there where is it? Derivative. First function. Yes. I should go back up and fill in. Oh, yeah, I said f prime of c is bigger than 0. That's one of the assumptions here. So this thing right here is an assumption in the inverse function theorem. F prime exists and f prime of c is bigger than 0 at c. Okay. I stated it carefully last time, and now this time I wanted to finish up the proof, which I claim is a snap. Sorry I get tongue-tied when I try to explain it. But questions about it? Okay, let's see. I guess it's a good moment to do some applications of this fact. Let's see, here's how to remember the formula. How to remember. This is such an easy way to remember it that that's why I can forget this formula. So how to remember that the inverse derivative at f of c is equal to 1 over f of prime of c. That's right. I've been writing g equals f inverse. So that means that g of f of x is equal to x. And the way to remember this formula is just to write that down and do the chain rule. g prime of f of x times f prime of x equals d by dx of x, which is a big fat 1. And so I get the famous formula is that g prime of f of x equals 1 over f prime of x. Check. Another way to write it would be, let's see. See, I've got that. I could, if I let the g of f of x, if I called that y, then the x would be equal to inverse of, that would be equal to, x would be equal to g of y. And so another way to write this formula would be g prime of y equals 1 over f prime of g of y. Same formula. Anyway, however you want to remember it, it's the chain rule. And so an example of where you would use such a thing, e to the x is an increasing function. Increasing monotone. Yeah, it's strictly increasing. Strictly increasing. And of course, it's continuous and differentiable. It's differentiable. And that, of course, that implies it's continuous. And its derivative is always positive. D by dx of e to the x is itself, and that's always positive. So the inverse exists. So the log function exists. The natural log function f of ln x exists and is differentiable. By the inverse function theorem. Let's see, the e to the x is an increasing function. It's really small over here. It goes through 1, and then it gets gigantic. And the log function, if I want to graph it on the same graph, I would get it by reflecting about the line y equals x. And so the log function would look like that. And let's see, these two things are symmetric about the line y equals x. I added that graph to the lecture where I talked about these things at the end. And log x only makes sense for x bigger than 0. Because you notice that e to the x is never negative. It's always positive. Anyway, now you can do things like calculate the derivative of the log function without knowing anything, without doing anything. Namely, because you know that, that's right, e to the log of x is equal to x. So when I differentiate that and use the chain rule, I would get, let's see, d by dy. The chain rule would say let's see, the derivative of e to the log e to the something is e to the something. So the chain rule would say this is e to the log x times d by dx of log x equals 1. And so we see that d by dx of log of x is 1 over e to the log of x, which is 1 over x. Famous formula you know from freshman calculus. Similarly, you can do the same thing with the arc sine function. Questions about that? Feels like freshman calculus again, probably. Let's think of y equals sine of x. I need to make it increasing. And sine of x, of course, it goes up and down. It's increasing and decreasing. But between minus pi over 2 and pi over 2, sine of x is strictly increasing. And its derivative is cosine x, which is strictly positive. So that's y equals sine of x. And the arc sine of x would be the inverse of that function. Okay, and then let's see, I'll graph it on this thing. Oh, let's see. Yeah, to get the graph, I'd have to flip it and do a 45-degree thing. Let's see, this goes from minus 1 to plus 1. And so when I do the 45-degree thing and flip it, I get a function that looks like an s going the other way. That would go, and this would go from minus 1 to plus 1. And these things on the x-axis and the y-axis would be minus pi over 2 to plus pi over 2. And that's the graph of y equals the arc sine. And I could do that same trick. Well, let's see, I have to use some other stuff. I guess I'll do it. Famous fact is that d by dx of the arc sine of x 1 over the square root of 1 minus x squared. Maybe I'll skip the details. So the proof of that would be chain rule. Like above. Another thing you need to know is that d by dx of the sine function is the cosine function. I haven't proved that, but you've seen that kind of thing a million times in all your classes. So that's another step. And then the final step to get that square root thing is to know that chain rule that sine squared plus cosine squared is 1. If you know those three things, you get the famous formula in a couple steps. Okay, now I finished off the last section. Now the present section is 6.2 on the mean value theorem. And now that we know a lot more than we did when you were a freshman in calculus, we can be careful about it and give proofs that would convince anybody about the truth of these things. And also we'll see a little bit more about why they're useful. So to rev up to the mean value theorem, here's an easy fact. If f has a local max, see, the book calls that a relative max. I still like to call it a local max. Let's see, the book calls that a relative max. So it has a local max at C, and it's differentiable there. Then that derivative has to be 0. Okay, and remark, the same would be true for mins. So the book does both cases in one sentence by saying a relative extremum, max or min. Okay, it's easy. It's an easy fact. In fact, I'm just going to give a picture proof of it. So let's take a point C here. And a local max just means, let's see, the function might be going kind of weird. Could be bigger over here, but there's an interval like that. So it could be bigger over there, but there's an interval here where the biggest point around is at C. Okay, that's going to be a local max. That's a local max. And a weird thing, let me draw something that also has a local max, but then I'm going to erase it. Oh, let's see. It could look like it could be really weird. There could be lots of maxes, but it never gets bigger than that max. It assumes that value there, and but it never gets bigger than that in this little interval about C. So it's a local max. Notice that it does get bigger to the left of that interval. So there's an interval where it looks like that. I'll erase this orange stuff. Okay, and then if you look at that, look at the difference quotient on the left. The difference quotient on left would be, let's see, f of x minus f of c over x minus c. Okay, f of c is the biggest one, is the biggest thing, and so f of x minus f of c is negative. And let's see, x is to the, so x on the left, x minus c would also be negative. So the denominator is also negative. And so the difference quotient, let's see, this would be less than or equal to 0. My orange thing showed you that it could be equal to 0 at lots of spots. So less than or equal to 0 divided by less than 0 is greater than or equal to 0. Okay. And when you think about the difference quotient on the right, we'd have f of x minus f of c. Well, f of c is the biggest one around. So that thing is still less than or equal to 0 on top. But now when x is to the right, x minus c would be positive. And less than or equal to 0 divided by positive is less than or equal to 0. Okay, so, and we know that that limit exists if and only if the left-hand limit is equal to the right-hand limit. So the limit of the difference quotient as x tends to c from the left is greater or equal to 0, and the limit as x tends to c from the positive side is less than or equal to 0. And if the derivatives exist, those two things must be equal. And of course, the only way for a greater than or equal zero number to be equal to a less than or equal to zero, they both must be zero. So that's all there is to that. It's a picture proof. Well, that leads us to a famous thing called Rolle's theorem. Let's suppose f is continuous on closed interval and differentiable inside and suppose it's f0 on the endpoints. F of a equals f of b equals 0. Then there's at least one point in the middle somewhere. Let's say differentiable inside. I should say differentiable on the inside, which is the open interval AB. Then there is a C between A and B where the derivative vanishes. A C with A less than C less than B, so strictly in the middle there somewhere, where f prime of C equals 0. The proof is going to be a snap. We know that f assumes its max and its min. It's max and min on AB. Because it's continuous. Okay. Well, let's see. A dumb case would be that the max and min are both 0. Dumb case, the max equals the min, and they're 0. Then f is identically 0. And of course, the derivative is 0 in the inside. Every c in between works. All c work. Now I think I'll draw a picture for the rest rather than say all these words. Here, let's say the case O. That's the dumb case. Let's do the case the max is greater than 0. Then the picture is function is 0 at A and B. The max, it has a max, who knows what else it does. That's the C. Let's see, the max would be strict, this C would be, it wouldn't be A or B because it's strictly positive there. And the little easy fact I said above, we know the derivative at a max has to be 0. So that's the max. And so the derivative at that max has to be, it's a local max, it's a global max, in fact. Okay. Then the case that the max is equal to 0, then it would always be negative, and it's not identically 0. Let's see, the case max equals 0. The picture would be let's make the case max less than or equal to 0. Then I'm going to use the min instead of the max. I could make this come up and be 0 here if I wanted to. A, B. Now I use the min. This would be the min, and it would be strictly less than 0. Because the dumb case is that f is constant. If it's not constant, it would go negative at some point. Anyway, there's a picture proof. The book gives you a paragraph where maybe it does it more carefully and uses more words, but no pictures. Anyway, it's all about knowing there's a max and a min. If the max is positive, then the slope would be 0 there. If you don't have that, then you have to deal with the min. Another standard trick in books is, let's say I was going to write a book and I wanted to use as few words as possible. The dumb case is still the dumb case. If the max is positive, I do that. If it's not positive, I take minus the function. And minus the function would have a positive max. And then I could use the previous case and see that minus f prime of c is 0. Well, that shows that f prime of c is equal to 0 too. So that's another way to do it. If you're trying to make a shortest proof in a book, you possibly can. Questions about that? It's easy to understand. But now the Rolle's theorem is the freshman calculus thing you see to rev you up for the mean value theorem. So we suppose that f is continuous on a closed interval and differentiable inside on the open interval AB. Then there is a C strictly between A and B, A less than C less than B, where f of B minus f of A over B minus A is equal to f prime of C. You might ask yourself, why is this called the mean value theorem? Think in terms of distance and speed. Let's say B is Indianapolis and A is West Lafayette. Then the distance to and B, the A and the B's are times. So let's say the distance is 0 at West Lafayette and 65 miles at Indianapolis. Then the numerator would be 65 miles, and the bottom would be the amount of time you take to get there. So that's 65 miles per, let's measure in hours. 65 miles divided by hours. And that would say at some point during the drive, you're going exactly your average speed. So the mean here is this is the average speed. Well, let's say average velocity. and this is the instantaneous velocity. So your average, there'd be a moment, at least one moment, might be lots of moments, especially if you're going at constant speed. But at least there's at least one time when you're going your average velocity. That's why it's called mean value theorem. Famous picture you see in all the calculus books. Let's see, I want to make it have a bulge. Okay, here's a chord. Here's f of a. Here's f of b up here. Here's a and b. And you see there's two spots in that picture where the slope of the secant would be equal to the instantaneous slope of the tangent vector. I'll try to make it a little bit better looking. This one would also be a good C. So that's a perfectly good C there. Pretty close to B, though. Another C would be perfectly fine there. And let's see, if I was going to demonstrate this, I'm not going to do the gory details that the book does. I'll raise this. Think about this. Think about turning Rolle's theorem sideways. This is the distance from Rolle's theorem right here. I'll make it orange. That perpendicular distance right there. Okay, I would use Rolle's theorem on that orange distance. And notice that orange distance would be continuous and differentiable, etc. That's pretty easy to figure out. And it would be max or min exactly when this distance would be max or min. Because those two, by similar triangles, those two distances are proportional by some trigonometric multiple. My colors aren't working very good here. What color? Maybe make this light green. The orange line and the green line and the orange line are proportional. Let's see if I divide. Let's see, that's a right triangle. So this is a right angle. So in fact, the orange line over the green line would be, what is that? That's the tangent of, what is that thing? Oh, orange line over the green line. Yeah, it's the sine of that angle between the vertical and the slope, the secant. Equal to a sine of an angle. And so they achieve the max at exactly the same value. So what the book does is it writes a formula for the green line, which is an easy thing to do. The green line length, that would be f of x minus the value of the function along the secant. Let's see, what would it be? The slope of that secant is f of b minus f of a over b minus a. And And this would be, you multiply by x minus a over b minus a. That slope, yeah, that would give it to you. So the green line distance is that. And you expect it to achieve its max exactly at the orange line. And that would be, in the picture, that would give you that slope you want there. Okay, so I'm not going to do the details. You expect it to happen, and it does happen. So read the proof carefully in the book. That's my motivation for the proof. Let's see. In freshman calculus, we spend a whole lecture on the mean value theorem. And it's hard to convince freshmen that this is an important thing. But Math 341 is about how do we know what we think we know. In freshmen, it's hard to convince them that it's important to think about those things. But I'm trying to convince freshmen this is important, and I should demonstrate this theorem. If your velocity is 0, you're not going anywhere. You're not moving. And of course, everybody knows that. So why the heck do you have to think about it? But the mean, if you ask somebody to prove it to you, it's the mean value theorem that would give you the proof. The mean value theorem, f of b minus f of a over b minus a would be equal to f prime of c, and if your velocity is 0, this would be 0. And so that shows you that f of b would be equal to f of a. That means you're not going anywhere. And you can do that on any interval. So that's how you know what you think you know. But it's also a surprisingly useful theorem when you're estimating functions. So let's suppose an important picture. If f prime of x is always bounded by something. So we're assuming f prime of x exists and is bounded by something. Then the picture here would be, especially in differential equations, you see this picture all the time. Let's suppose f of c is, you know. I'll put a c here. And f of c is going to be right here. And the mean value theorem is going to tell me that this function is stuck between lines that look like this. This line is going to have slope plus m. This line is going to have slope minus m. And the function, the graph of the function, is squeezed between these two lines. It could be, let's see, I don't think. It can't get out of those two lines. If it was identically equal to m plus m, it would be stuck on the top line. If it was always is equal to minus m, it'd be stuck on the minus on the other line. And if it's between, then it's stuck between those lines. So the picture is f of x is stuck in the wedge. Another way to use the mean value theorem is to see how closely the linear approximation, so f of x, is approximately equal. This is the best linear approximation, f of c plus f prime of c times x minus c. That's the best linear approximation to f. Near c. And you can use the mean value theorem to estimate that error. The error of the approximation. In fact, if you look at it there, that kind of see the mean value theorem kind of staring you in the face. Well, I'm not going to have time to talk about Darboux's theorem today, but it's a fascinating thing. French I want to state it. I can state it. Let's see if f is differentiable on a closed interval and if k is between f prime of A and f prime of B, then there's a point between where f prime is k. So there's a C between A and B with f prime of C equal k. It just looks like an intermediate value theorem. But we don't know that f prime is continuous. So proof, it looks like the intermediate value theorem. So I'll put question mark. It's not the intermediate value theorem because we haven't assumed that f prime is continuous. So you have to do something fancier. The proof is a fancy application of the mean value theorem. It's not terribly fancy. It's just couple sentences long, but I don't have time to do it in 1 minute. So I'll say tricky use of the mean value theorem. Anyway, read it. It's not hard, and it's an interesting fact that you get a mean value theorem for derivatives even though you don't assume the derivatives are continuous. Of course, if they were continuous, you could use the mean value theorem.